بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so welcome to the lecture 3 about the Internet of Things architecture. In the previous lecture we have made a brief introduction to the IoT and the different type of applications, the different type of sensors, and we have discussed also some of the challenges to build IoT application. In this lecture you will get introduced to the architecture of an IoT. So architecture, it means what are the different players, what are the different components that we find in an IoT ecosystem. And this is very important to know because at the end of the course you are so you will learn how to build an IoT application. So you must know all the different pipelines through which an IoT application is going to operate. So the learning outcome of this lecture, first of all, you will understand the IoT architecture layers, different layers of the IoT architecture, including the sensor layer, the networking layer, the middleware layer, and the interaction. Why we need all these different layers to build an IoT application. Because basically building an IoT application, we're talking about a huge scale of a lot of sensors that will be sending data to servers, and we need to analyze this data, visualize this data, share this data among several different type of users. There are different computing paradigms that we need to understand also in the context of IoT, and namely this is called the edge computing, fog computing, or cloud computing. Probably most of you have already heard about cloud, but I'm not sure whether you have heard about edge computing or fog computing. So I will illustrate these concepts to you during this lecture, and I will also explore some of the existing middleware solutions. And middleware مثل الوسيط يعني it's going to mediate between the sensors and the applications or the end users. Okay, so it will be able to exchange the data that we will send through the internet to be dispatched over different users or services. So the lecture outline, I'm going to start with presenting the IoT architecture in general, and then the sensor layers, the communication and networking layer, the middleware layer, and finally I will explain the IoT computing paradigm. Okay, so what are the different components of an IoT architecture? So tell me what do you observe here? Let's try to understand together this picture. Yes? What do you see in this picture? Nothing?
Sensors that connect to the gateway.
So we have sensors. Okay, what is the objective of sensors? What do they do?
Sensor physical activity.
Processing data, but there is another role of the sensor, more than processing. Yeah, they can process the data, but still they collect the data. We talk about data collection. Okay, and read Jamal Bayanet. So sensors, they have the ability to provide you the data from the environment. For example, a temperature sensor can provide you information about the heat, okay? And this can be used, for example, to detect fires, if there is a fire, or smoke detector. So sensors is one of the most important core components of an IoT, and the objective is to collect data. What we can see, so now imagine that you collected data. What do you need to do with this data? Process the data, yes. So how do we process? Where do we process it first? Locally? Yeah, we can process it on the cloud. Let's say we want to process either local or remote. We can process locally. I can have a sensor device attached to a computer, and I can process this sensor information locally. So this computer that is connected to a sensor, usually we call it an edge. موجود على الحافة على الأطراف. Okay? And this is what we call edge computing, is when we compute or we process the sensing information directly into a computer that is close to the sensor. And this can be, for example, an Arduino or a Raspberry Pi or something similar. Usually they are small devices that does not consume power. I'm not going to connect a server to a small device, because usually a small device is going to generate small amount of information. Okay, of course, some of the devices like camera, they can generate, heavy data like video stream. But now even with edge devices like Jetson boards, I don't know if you have heard about Jetson Nano, or Xavier, they have GPU capabilities. They are small devices with GPU capabilities, and they are able also to process like images or video streams inside. Okay, so we can process on board or on the edge. We can also process remotely. And remotely, what is remotely? So maybe the keyword that you know is on the cloud. And the cloud for you is kind of server, which is remotely placed like in Amazon or in Google, probably STC, or any kind of cloud provider, where, it's used to process data. But not only for processing. What do we do in cloud as well? Storage. Okay, so all our mobile phone data, for example, all your pictures are stored either in Apple or in Google Cloud. So cloud is basically for data management, including storage, processing, manipulation, retrieval. Okay, so all of these things, we can do them in the cloud. Of course, now we have two concepts, edge and cloud, which is sufficient for the moment. Yeah, what we can do also in the cloud, we can do big data processing, because usually the cloud is a repository where we collect a huge amount of data, and this data is usually unstructured. What does it mean, unstructured data? Unstructured data, yes. ايه مثلا structured data ممكن يكون جداول table مثل database. This is kind of structured data. It has number of rows, number of columns. Like an Excel sheet is structured data, CSV file is structured data. But when you have a cloud with images, sounds, files, Word documents, PDF documents, any kind of data, this data is completely unstructured. They are different type. They have different types, different categories. So this makes the problem of big data processing even more challenging. And the cloud usually it has different type of tools to manipulate this heterogeneous type of data. So what do we see else? Now we are exploring the IoT architecture, which is excellent. Yes. What else? Yeah. Another component. So how do we manipulate IoT data in your device? You need to have a web application or a mobile application, okay, to visualize, to get insights of the data. So you're going to have sensor that will generate data, and this data could be raw data that you cannot even understand. Imagine that the sensor will generate a signal or a voice or sound. So usually you need to visualize it in properly. You need to make a data transformation to visualize it maybe in mobile app or web app and so on. Okay, and we got now the sensing part, the data collection part, the data manipulation part, the data visualization part, but we missed one part, which is communication. Okay, so communication here, it involves different type of networking protocols, communication protocols, like Wi-Fi. We can use Wi-Fi to transfer data. We can use 5G if I want to submit to something remote. Okay, we can use wired communication, optical fibers. So there are different ways on how we can transfer data over the internet or over the network. And this is another layer that is part of the communication layer. So networking and communication is one layer, but now we will have maybe millions or billions or trillions of sensors connected everywhere. So imagine now Google Cloud, how many data they are collected every millisecond. I don't say every second, but every millisecond, how many data they are collected. So how can they manage that all this data, all this traffic is going to come to their cloud properly? Imagine now that all the people would like to go all together. Imagine that when people go out of the stadium and they want to go outside, you can imagine the whole traffic. So what do we need? We need to have proper routing so that there is no collisions. All this traffic can be well routed, and this is why we need middleware. So middleware هو عبارة على محول that can manage a huge amount of data or massive data to be routed on the internet while reducing bottlenecks, improving efficiency, and improving quality of service. Okay, So basically now in this slide, we have summarized all the different components, including sensing, cloud processing, data storage and manipulation, control and analytics. Okay, we can have data analytics, user interfaces, and also we have another non-functional properties, which are administration of the data and security. This data is personal. It can come from your mobile phone or a camera that is connected in your house. You don't want to have other people to see within your house. So this data has to be encrypted, has to be secured. So there is a complete, a security challenge to secure all this data that comes through the internet. And if you remember in the last two lectures, we have discussed a lot the issue of privacy. Privacy is a big issue. And I don't believe that there is a privacy when your data flows over the internet. There is always a possibility that your data could be manipulated by others. Okay. So look at this slide. This slide is an illustration of an application that follows the same IoT architecture. This is one of our previous work to detect red palm beetle. I've talked about this in the previous lectures. And we wanted to build an IoT architecture that will allow us to monitor red palm beetle on the farms, okay, where we could be located. I'm not going to stay all the time in the farm just looking for these sensors. I need to collect this data from the sensors. Okay, so we can imagine that we have different type of sensors. A drone can be considered as a sensor. If you imagine a drone with a camera, it could be an RGB camera, or it could be hyperspectral camera. So there are special cameras that we can put on the drone. They can tell us about the health of the palms or the health of the crop. And this can collect data and then send it through the internet. We can have sensors also plugged into the palm trees to check whether there is an insect that is eating inside the palm. Of course, now this is the part of data collection, and we need to transfer this data to the internet. So here we could have some steps. So imagine that I can put a sensor with Wi-Fi chip on it. That's possible. But what is the drawback? So usually Wi-Fi consumes a lot of power consumption. Okay. Now even 5G, for example, if you use a lot of 5G, you connect to YouTube or I don't know, or to the internet with your mobile phone, you will observe that the energy will be dissipated quite fast. Okay, and it's not possible that we are going to recharge the sensor node at daily basis. There are some ways that we can put solar panel connected to each sensor node, but solar panel are also expensive and heavy. So it's not really common to put sensor nodes. So we need to utilize or use low power energy consumption, and we need to reduce the communication energy. How we can do that? So one protocol that is called LoRa, it allows to send through long ranges and smaller, doesn't dissipate too much energy. So this is why here we use LoRa, and we can have LoRa gateway. So LoRa gateway, they are going to receive the message from LoRa communication, and then we'll transfer it to the internet either through an Ethernet cable or 4G or 5G communication. And if it reaches to 4G and 5G, I can send it everywhere. I can send it to the cloud. It can be a Google cloud, can be an Amazon cloud, can be an SEC cloud, where I have all my data stored here, and then I can make a visualization to the end users, to the farmers. If they can observe, probably I have an insect activity within this palm, so I need to take an action. We can have an alarm, so we can trigger alarms when we can detect an activity over this palm activity. So here we need to care about connectivity, how we can connect like large farms with, for example, LoRa gateway. They can provide us long ranges. We can do edge processing. Okay, so local filtering. We can do CoAP and MQTT protocols. These are application layer protocols at the sensor level. And we store our data in the cloud for later on visualize it to the end users. Voila. Any question? Okay. Okay, so that's the summary. We're going to talk about the sensor layer, communication layer, middleware layer, and application layer, and cloud and fog layers. Yes?
LoRa is a middleware layer, right?
LoRa is a communication protocol, like Wi-Fi. Okay, so it is an alternative to Wi-Fi that we can use with sensor nodes that have low power requirements. Okay?
Consumes less energy, like?
Yes. So there are different requirements for communication. So usually in sensor network, we don't require high bandwidth. It's only small amount of data that we send occasionally. So these protocols were designed for these type of scenarios so that they don't consume much energy. Yes. Okay, so for the sensor layer, we did talk about this, that the role of sensor is primary source of data collection. It's basically is to collect data from these sensors, from the environment. And it's a way on how to convert signals into a digital data. Because what is a sensor? It's a physical device that will have a reaction to certain event. Okay, so this reaction is going to generate a signal. And based on this signal, we can either detect that there is an event or not. Infrared, for example. So infrared is going to send an infrared signal, and later on we will have a reflection when there is an obstacle that will cross through that radiation. And based on the single fingerprint from the obstacle, we can detect whether there is a motion or no motion. This is the way how motion sensor worked in practice. So the sensor, besides data collection, it's able to convert a signal into a digital data that we can send. Same thing, for example, for the temperature. Okay, we will have a sensor that will react to the temperature, and based on this, is going to convert it to a value, okay, so that we can read it later on. Because we, as human, we cannot read signals. We don't have any understanding. So there are some single processing techniques or signal processing techniques that will convert the signal into a digital value that will be later on sent to the internet. So the sensor basically is going to convert these signals into a data that later on will be sent over the wire. Okay, this is an example of accelerometer and gyroscope data. This is how we get the signals. It's basically a wave. Can anybody understand what this signal refers to? We don't. But we need to use signal processing techniques or machine learning techniques to convert this signal, because these signals will have patterns. يكون عندهم خصائص. Okay, مثلا with accelerometer data we are able to detect human activity, whether a human is walking, is sleeping, or is running, based on signal processing and signal transformation into an insightful data. So this is how a sensor data will look like. It can be a continuous signal, it can be kind of noise-like signal, but later on all these signals would have patterns. And these patterns, using some machine learning techniques or artificial intelligence approaches, we can convert them into some meaningful information. So the objective is to collect the raw data from the environment and then process it in order to get insights from there. So let's look at the different type of sensors that we can have in practice. So we can have environmental sensors like temperature, humidity, and light. And these are different type of sensors. For example, this is a humidity sensor. Tell us what is the ambient humidity in the environment. This sensor is for air pressure. All of them are from environment. This is an alcohol sensor. This is ultrasonic sensor. So this ultrasonic sensor is kind of range sensor, مثل الرادار. Okay, so usually these sensors have small range, maybe 5 meters, 10 meters maximum. Okay, usually it's for proximity range detection. Touch sensor, this is like a button. When you press over it, this sensor able to detect between colors. Soil sensor, this is for agriculture. It can tell us about one of the things is for example moisture, but it can have the pH of the soil. Okay, so usually the pH should be something below, a little bit below 7, for the plant to absorb the nutrition from the soil. If you have a very alkaline soil, it means that it's not going to be able to absorb. ولذلك نزيدوا الفرتلايزر. Fertilizer is basically increase the acidity of the soil. So this helps to measure this type of information. We can have gas sensors, for example, for gas leak detection, sound sensors, tilt sensors. You can see different type of sensors, and can be used in applications like motions, health, or industrial sensors. That's an amazing application. This is a company in Tunisia. It's called Mumi, and they have developed a funny application, very interesting actually for farmers who have cows. You know that cows are expensive, and you know it's a big asset for farming. So they can put like a collar in the cow to monitor its activities. And with collaboration with the farmers, they have understand that, you know, and this cow is basically an accelerometer sensor. So it will generate signals like this. But they use machine learning techniques to convert these signals to understand the health of the cow and its activity. Okay? The cow, for example, it has certain hours per day it has to be eating, الاشترار أو الجلوس أو المشي, so they can monitor this. For example, if a cow doesn't walk as often as it used to do or it has to do, so we can detect that probably there is an issue. And this is very helpful for people who have thousands of cows or maybe even more. So we can monitor every cow individually through an interface. We can receive an alarm whether there is a problem with the health issues of a particular cow. And all of this is by analyzing this data. So this data might look like a noise, but using advanced signal processing techniques and machine learning techniques, we are able to convert it into a meaningful information. And so, of course, there are some also requirements, like the color has to be waterproof, and this is IP67. It's one of the standards for waterproofing that you can find it in some outdoor devices like cameras and so on. Okay, it detects heat and also provide AI warning to provide alert for the heat cycle, and also allows real-time monitoring. So you can monitor, they can monitor the crop in real time. So coming back to the red pan weevil, now the problem with the sensors is that they will provide us raw data similar to this one, which is not interpretable by humans. And the objective is that we perform also the data manipulation or data transformation. Imagine that I collect a signal like this, and at the end, I would like to have a signal or an alarm whether the palm is infected or not infected. Okay, so the objective here is to convert a sound signal using machine learning techniques. This is one of the research work that we have done to convert the noise that we receive from the sensors to classify this noise, whether it is a noise related to an infestation or a normal activity. First, now we take 20-second sequence of sound. في عندنا sound sensor دخلوه في البال, and we collect windows of 20 seconds. And then we do, of course, now we know in advance that these 20 seconds corresponds to a red pan weevil infestation. So we have kind of labeled data. We know the data that is related to infestation and the data that is not related to infestation. And based on this, we train a machine learning model or a deep learning model. We do a transformation, initial transformation of the data, then train it on a neural network to finally classify this raw data into a classification of infestation or non-infestation. Okay, so it's really important that when you collect your raw data, you have the ability to convert this data into information that is relevant to visualize by the user. So that's another also example from raw data. This is a raw data, 6 hours of data collection on red pan weevil. This is without infestation and this is with infestation. In this work, we didn't do machine learning technique, but we did hyperspectral analysis. Okay, so we can observe here when doing the statistical analysis of the data that the distribution of the histograms are different. So how do we interpret that this corresponds to red pan weevil? لأنه الvariation when there is an insect that is making noise inside the pan, so the variation of the sound will be higher. مش لما يكون هناك silence. Okay, so based on the variance, you are able to understand whether the signal correspond to an infestation or non-infestation. لأنه لو فرضنا ما عندكش variance, so in this case, you don't have any change in the sound. So it means that there is no activity. But of course, this is not very reliable. لأنه يمكن يجي, we can have noise from another source, not necessarily from the red pan weevil. So here we can detect whether there is a noise or not a noise. But now the classification of the signal itself, using machine learning technique, it provides us something real 100% of accuracy. واضح؟ Okay. So the second layer is about communication in IoT. And communication is actually the lifeline of Internet of Things. هي اللي تمد الحساسات بالحياة لأنها تربطها مع العالم الخارجي. If you don't have communication, there is no external communication with others. So it's basically through the internet that everything happens. But before reaching the internet, we need to have some communication protocols like Zigbee or Sigfox, low power communication protocols attached to the devices. And then we reach the internet, and finally we store the data at central repository, whether they are cloud computing systems or others. So the communication is essential because it connects sensor devices and systems for seamless data exchange. They enable real-time monitoring and control and automation, and also facilitate the decision making through data sharing and analysis. But there are some challenges because IoT applications, they have different type of requirements. So imagine that I want to use IoT for making remote surgery over the internet, which requires cameras and high-level sensors. What are the requirements in this case? Surgery, مش هعمل عملية الآن في بعض الأطباء يعملوا عملية عن طريق الإنترنت. Yes, موجود. Online, yes. عملية جراحية. طبيب في أمريكا يعمل في عملية في الصين. موجودة سويها على اليوتيوب. 5G communication هذه صارت من 5 سنوات. أول ما خرج ال 5G الصين قامت بها. Yes. طبيب يسوي عملية. العملية عن طريق نعم عنده ديفايس يحركه وتتحرك في نفس الوقت على المريض نفسه. This happens. This happened already. It's not something new. I talked about 5 years ago. Okay, what are the requirements here? هذه عملية فيها حياة أو موت. طبعا مش يكون عندنا انرجي يس. أهم شيء latency. تخيل الطبيب مش يعمل شيء وتوصل متأخر يعني يكون يقضي على المريض نهائيا فلازم يكون in real time. يعني real time requirement, it's crucial in this case. Okay, this is an example of an IoT application. Here we have the primary concern is about the latency because this is a time sensitive, it's life critical application, not only time sensitive application. Okay, for industrial automation, telemedicine is the application as I mentioned now. Okay, ensuring immediate response time. We need to have immediate. وذاك على style 5G. 5G when it was proposed is to allow real-time high bandwidth communication. الآن 5G it has much higher bandwidth than 4G and it has lower latency. And this is in theory لأنه البيز station they are closer to the end user. استعملوا high power فلذلك there is lower risk of losing communication. So reliability in principle it's much higher than the 4G. اللي السيلز فيها تبدأ أكبر من 5G. That's one thing. Now imagine that you want to monitor agriculture devices. You have soil sensors موجودين and they collect data. do they have the same requirement? عندي حساسات في الأرض يقيسوا مستوى الرطوبة. What are the requirements here? What do you care about? Do you care about latency? Yeah, because the data is not going to change immediately. If you take a measurement now, you can take a measurement after 1 hour. Okay? After 30 minutes في الصيف مثلا بتشوف المويستشر مدى رطوبة الأرض. لكن what do you care about more? You'll put your sensors there. You care about the energy consumption. You don't want to change the battery every day. You want to keep the sensor maybe for 1 year, 2 years without any change. So you can see it's an IoT application, but completely a different requirement. So sometimes we care about energy efficiency, where we need to save energy. In other cases, we care more about the latency. Okay, in self-driving cars, we have sensors. Okay, so we don't tolerate latency at all. Because, for example, if a LiDAR will see an obstacle, I must take a decision to stop the car immediately. Otherwise, we can have a crash or an accident against pedestrians or against other type of obstacles. Okay, high scalability. This is also important because several IoT applications, they require the deployment of millions or maybe trillions of sensors worldwide and collect them. Some other applications will require reliability. It means that I don't tolerate any error. مثل العملية الجراحية مثلا. It's highly, yes, there is a high reliability requirement. Okay, so in this case, we need to have consistent and error-free data delivery to maintain integrity even in challenging network conditions. And this is not easy because you communicate through the internet. ممكن تقطع عليك الانترنت. It's possible. So you need to have fault tolerance mechanism. If the internet, for example, stops, what should I do in order to avoid, for example, fatal consequences? And protocol interoperability, it's because different type of devices, they are going to communicate over the globe all together, so they need to be interoperable. And for this, we use standard protocols like MQTT or CoAP or ZigBee. These are different types of communication protocols and application layer protocols on the internet. So this slide summarizes also conflicting networking requirement in the IoT. So look here, you have on the x-axis, you have the bandwidth throughput. الاحتياج في الباندويث. وهنا الاحتياج في الديلي. So here I need only very short delay, and then I can tolerate up to 1 second. And here only 1 millisecond. Look مثلا, if I consider virtual reality is based on video, on gaming, so it requires high bandwidth, over 1 gigabyte of bandwidth. But at the same time, because you will play on the internet, you need to have very short delay. Okay, if you want to monitor sensor network, so usually sensor will send small amount of data, so I need only less than 1 megabyte per second bandwidth, and they can tolerate up to 1 second because usually this, okay, depending on the sensor, if they are sending critical information or not, but usually in smart homes and so on, 1 second, 2 seconds, even a couple of seconds is not a big deal. So these are two extreme situations, and then you can have different type of requirements like video streaming, personal cloud, real-time gaming. Okay, you need high bandwidth, but probably not at the time of 1 gigabyte. It's almost something around 10, and you need 10 milliseconds of delay. That will be sufficient. Okay, just for the game not to lag over the network. And you have different type of application, fixed application, like you have fixed sensors, they don't move, they are static, or nomadic, like self-driving cars, or like video streaming, real-time gaming. They can come sometimes and being on and off, and you have also on-the-go type of applications. So in terms of requirement consideration, now there are different categories of requirement. We have technical requirement, commercial requirement, and ecosystem factors. So technical requirement is, as we talked about them, energy efficiency, latency, throughput, coverage. These are technical requirements from technical perspective. Now, if you are an IoT engineer and you will deploy an application, you will think about these requirements. Should I have power efficiency or real-time constraints or bandwidth or coverage? So this is what an IoT engineer will be considering when designing an application. Now, if you do a business on IoT, you don't care about this. You will give it to your engineer and say, how much is it going to cost me? You deploy sensors. So there is a cost because you're doing a business. And this is part of the commercial. Quality of service. Okay, how long is it going to take for the signal to reach? And this is common, actually. With latency is always an issue, especially if we have some stringent constraints. From commercial perspective, you will care about security. Okay, I don't want my data to be hacked by others. And also scalability, how many sensors I can deploy into my application. So to maximize the gain. And from ecosystem factor, okay, we have to ensure the long-term sustainability of these devices, and also we ensure global reach and interoperability between different systems. Okay, let's move on to the middleware layer. So now we talked about the sensor, we talked about the communication and networking, and you want to dispatch this information over the internet. Of course, we're talking about a huge amount of data coming at the same time. You know, we have sensors everywhere. Imagine that every one of you has mobile phone. It's a sensor. It's sending data right now, either to Apple or Google or someone. Okay, if we don't manage this traffic in a proper way, there will be a lot of bottleneck in the servers. And this is why we need special type of systems that we call middleware. They come in the middle. Maybe in the IoT devices, maybe in the cloud. What do? They will dispatch the traffic. So dispatching. شفتوا ذاك مفترق الطرقات السيارات وكل. It's basically the same thing. It will tell, oh, you have to go from this way, the other one has to go from this way. Okay, and there are different type of middlewares that will allow the exchange of messages over an IoT system. Okay, to improve interoperability of the devices, to make a bridge, okay, between devices and applications, and also for better data management. Okay, they manage the data flow, the device communication, and also making much easier for system integration. You have sensors that come from this vendor, from another vendor. They communicate with different type of protocols, and you want to make an integration. So middleware, it helps mitigate all this issue from development perspective. And scalability, they will allow to dispatch millions or billions or even trillions of data at the same time. So this is why we need to have middleware to ensure these benefits. And their function, they perform device management. Okay, so they help monitoring the state of the device, making updates on the device, and also setting up the devices. They have data processing, like aggregation, filtering. You know, I'm going to show you a demo. So usually we don't want to send all the data, raw data to the cloud. So sometimes, for example, if I have 10 sensors that are in a certain region co-located, I can take the average of these sensors and send only one information instead of sending 10 different data to the cloud. This is what we call aggregation. Sometimes we make filtering. If I have a value that is an outlier, I can filter this out, or I can tolerate certain range of data. So we can do data processing on the middleware. Formatting of the data, there is different type of formats, JSON format, XML format. So we can do formatting exchange. They can ensure security, they implement authentication, encryption. They can manage to have events like alerts. And it will make it easier for the developer to integrate with different systems, which we call API integration. Yes?
This happens in the system, in the IoT system.
Hmm?
The IoT system, does this happen? The filtering and the aggregation.
Yes, this happens into the middleware. الميدلوير هو الوسيط. Okay.
Between what and what? The sensor and what?
And the applications, the cloud. So before reaching the cloud, And even the cloud can have a middleware that will dispatch يعني يسوي exchange the messages. مثلا you have thousands of sensors and thousands of users, and there is one company that is providing this service. How do I know that this sensor has to go to this user and not to the other one? You see what I mean? Okay, so you need to have this type of middlewares that will ensure the data flow management. Okay, and it will inform you, for example, if you have a certain alarm into your sensor, that will inform you in your application, you have, for example, a certain event that is happening with that sensor.
It's not a system, it's an application.
It's like a networking system. Networking system.
Can you see it? Or what's,
Yeah, we will do some programming on this, yes. And let me show how it works. So this is an example of middleware system that is known as RabbitMQ, one of the most popular frameworks. It's a lightweight message broker. Broker يعني وسيط. Okay? Designed to handle asynchronous communication. Asynchronous يعني someone send, another one will listen at different times. Okay? This is what we call asynchronous. Between producer and consumers. Most of the IoT applications, they are based on a communication paradigm known as publish, subscribe. ايش معناها publish, subscribe? There is one node that will produce data. Imagine that you have a sensor node that provides temperature reading. This is a producer. Just keep sending every second the temperature is equal to this value continuously. This is a producer. And we will have consumers. Maybe you are measuring the temperature into your house. So you are a consumer. Your mobile app is a consumer. It's going to consume this application. And maybe not only you, your family members. So we can have multiple consumers, and you can have multiple producers. Your house could have multiple sensors plugged. Okay, temperature, humidity, I don't know, other things, or motion. So these systems, they are able to make an exchange. So the producer will send at any time. It's asynchronous. I can send at any time. And the consumer can consume at any time. So you will consume these messages when you open your application. Otherwise, there is no consumption. Your application is sleeping, not consuming this information. So here, the producer will be sending messages. This message is for the temperature. It's going to go to this queue. This is for motion sensor. It's going to go to this queue. Of course, there is a business logic on how we switch or do the exchange of messages among different queues. This is the exchange. And there are different communication patterns, but this is the most basic. You have a message produced, you have an exchange, you're going to put it on a queue, and you have a consumer. When it wakes up, you just pull the message and make use of it. واضحة الفكرة? And you can imagine that at a very huge scale, it's being done at microsecond level. So technically speaking, we talk about producer exchange. Binding, it means assigning a message into a queue. This is what we call binding. And you have queues. It's temporary buffer where to store images, and then will be consumed by a consumer. Yeah.
is the system of exchanging binding and queues is fixed throughout all middlewares, or does it differ?
The common thing in IoT middleware or IoT application in general is that always we have a producer and a consumer. The way how we do the exchange, this depends on the middleware logic. So this is RabbitMQ. It works in this way. And we have also Kafka. It works in a different way. That's another middleware. Same thing, we have producers and consumers. But the logic here is different. We don't have the concept of exchange, of queues. We have the concept of Kafka cluster. This is a cluster. And this is the coordinator of the cluster. We call it zookeeper. They call it in their terminology of Kafka. But this is kind of manager of brokers, al-wusata. Even the other one is a broker. Here we can have multiple brokers. And the data that will come is going to be stored as partitions. Okay? The data partition, each topic is divided into partitions. Why? To allow parallel processing and scalability. So people can, or consumer can read from this partition and this partition at the same time. So in this case, I can increase parallelism because it's one resource. If I have multiple consumers at the same time. So the first will take the message, the other one has to wait until it releases the resource. So when we do partitions in parallel way, we can actually increase the scalability of the system and improve the real-time responsiveness of the system. So the way how this middleware is built is completely different from Arbitrum, and these are two popular ones. These are the two main standards now used in IoT ecosystem to exchange messages over IoT devices. And you have consumers, the same thing is the application is gonna use the sensor data and make use of it. واضح؟ Okay, the last part of this lecture is about the IoT computing paradigms. خلينا نلخصه الآن. What did we learn? شكون يلخص لي الليكتشر كاملة؟ What is an IoT architecture?
That we have sensors that goes through the gateway to the cloud.
We have sensors. What do they do? What is the role of sensor?
They
Collect data. ممتاز. And
process the data.
process the data. Convert the signal into raw data. Okay, that's processing, kind of processing data. And then, okay, what we will do with this data? Communication. Yeah, we have to send it where? To the cloud. Okay, we send to the cloud. Let's be simple. We send to a server, that you can call it the cloud. And what does it do with the cloud? Process it. Save it. Okay, retrieve it if you want. Do data analytics. Send to the users. Okay, making dashboards. Can do plenty of things from the cloud. Okay, operating machine learning. And before reaching to the cloud, we need to use. What's the purpose of a middleware?
Guides the data to its specific place.
Why we don't send directly to the cloud?
So no collision or
Yeah, so it helps improving the scalability because we have a huge amount of data being sent. So the middleware, it's kind of ensure the smooth exchange of data between the consumers and the producers. واضح? And it's based on a publish subscribe mechanism. والمخالف publish subscribe is client server. Client server مختلف. When you have a client server, you are a client, you will connect to a server, you send a request, so the client will keep waiting. صح ولا لا؟ You will keep waiting until you receive a response. بعض الأحيان يمكن تقعد 1 second, 2 seconds, بعض الأحيان يمكن stay 1 minute. This is what we call synchronous. لكن with asynchronous, no. The publisher can send any time, the consumer can consume at any time. So it reduces there is no waiting. I'm not synchronized with the server. As a consumer, I'm not synchronized with the producer. Now, we have data, and in the beginning we said we can process the data locally, or we can process the data in the cloud. What if all the data will be processed in one cloud? Could we have an issue if we process تخيل كل البيانات السعودية نتاع الاي او تي one cloud تمشي مباشرة ل one cloud. ها؟ Yeah, we have problem. First of all, if the cloud fails, everything fails. We have single point of failure. ثاني حاجة, what's the other issue? Now we talk about IoT, we talk about massive data. Massive data in one cloud. What happens? Yes, stress. تخيل كل الناس الآن تدخل على الكلاود for consumer and producer. كل الاي او تي يوصل على هذا وكل الناس تسحب من نفس الكلاود. It's gonna die. Okay? Cannot. يا اما تكون الكلاود very expensive. You need to expand the resource and it's going to be very expensive. The latency will be high لأنه all people will have to go to the same. ممكن الكلاود هذا موجود في الرياض. الناس اللي موجودين في جدة ولا في الجنوب ولا في الشمال. They will have to go through different networks to reach. So we need to have different layers of computing. The edge, which is the closest to the sensor. The cloud is kind of the central repository. And you can have something in the middle that will mediate. Okay, for example, I have many edges. I collect from them and I process first locally into a fog and then into a cloud. Of course, here I have 3 layers, but the fog and the edge can be more layers. Like in these, to have a better understanding about the data distribution based on the scale. If I have a huge scale, of course, if I have small scale, an edge is sufficient. If I have a medium scale, I can have an edge in the cloud or edge or a fog. But if I have a huge scale, trillions of data, many and billions of users. So in this case, I can make fogs. So in every region, in every sector, I will have a certain server that is bigger than the edge and smaller than the cloud to process intermediate data. So this is how it looks like. So cloud computing is basically the centralized data processing and storage in remote servers. This is like the biggest server that we will have in our IoT ecosystem. The fog computing is the distributed computing closer to the edge, bridging the cloud and IoT devices. So this acts like bridges. This is one fog. Look, this fog is responsible for this cluster of edge devices. Second fog is responsible for this cluster. So we can make traffic distribution instead of sending everything to the cloud right away. So here I can do aggregation. I have different temperatures values. So I calculate the average here and send the average of all these clusters here. Okay? And let's see this in practice. So this is a demo. Let me show you the live demo. So here imagine that you have an edge layer, a fog layer, and a cloud layer. And this will emulate sensing information coming from different quarters, from Riyadh, from Jeddah, and so on. What will this be? If I consider individual sensors, مثلا بعض السنسور في الملز، بعض في حي الصحافة، في حي التعاون. So is this edge or fog or cloud?
What is the option?
I will put individual sensors في الأحياء، أحياء الرياض، أحياء جدة، أحياء مدن مختلفة. So this will be edge. Okay. And what will be the fog? Region معينة. Okay. And the cloud? National level مثلا. That's an example. Okay. Let's look at the simulation here. Okay. This simulates sensors. Look, I have a temperature sensor in Ulaya district in Riyadh. Another one, it's sensor. This is a temperature sensor or a humidity sensor. This is an air quality sensor in Ulaya district. So in Ulaya I have 3 sensors now. In Al-Malaz I have 3 other sensors. In Al-Balad, in Jeddah, I have other sensors. So we can consider this layer of sensors as the edge layer, because every sensor will produce raw data. And look, here I have 24, 55. We can have alerts of critical events like bad quality of air, bad air quality. And then imagine that مثلا لو نفترض وزارة البيئة ولا شيء يختص بالبيئة يكون عندهم سيرفرات في كل مدينة. So we can have a fog layer only looking at the central region or the Riyadh region. Another one is the western region. And they will be aggregating. They don't need to have the individual reading from every sensor. But I say now, in Ulaya district, I will have an average of 21 degrees. Okay, so if I assume that I have many sensors in Al-Ulaya, I'm going to aggregate all these sensors into one. And at the national level, so I will look at the average of the averages from Riyadh region, for example, and from Jeddah region or western region. We will have an aggregation, and here you can have a monitoring in a dashboard showing the variation of air quality. Look الآن مثلا لما نشوف air quality مثلا ارتفعت جدا, it can be an alert like you see here. There is a poor air quality, في pollution مثلا, يمكن انبعاث الغازات من السيارات وإلا something else happening. Okay, so this is an example of simulated data that goes from the edge layer into the cloud computing layer. Okay, so to summarize, the difference between cloud, fog, and edge, we can see it from different perspectives: processing location, latency, and the application. So in the cloud, the processing location is on the remote servers. On the fog is local network or gateway or something like it's in between the edge. The edge is attached to the IoT devices and between the central cloud. That's from the location perspective. The latency, okay, here the latency is high because usually it's a central repository. The latency here is medium because it's at a regional level. And here you have usually like physical connection between the sensor and the edge device. So you have low latency. And it's best for, we use the cloud for big data storage and analytics because it's the location where we can collect a huge amount of data. You cannot do data analytics on a Raspberry Pi. Okay, you need to have a huge server to process massive amount of data. So the fog is for distributed IoT systems to make load balancing of the IoT traffic among different servers. And the edge is for real-time tasks processing on the edge. For example, we can use an edge device for object classification attached to a camera. طبعا هذا في الماضي ما كانش ممكن، لكن الآن مع الجيتسون بوردز ولا راسبيري باي with GPU we are able to process data locally from IoT devices. Okay, so this is just a summary of what we have talked about. Now, cloud platforms, there are different type of cloud platforms, and probably we will work with some of them during this lecture, like AWS IoT Core. So it's an IoT cloud by Amazon, and it is good for device management and secure communication and analytics. Microsoft has also Microsoft Azure IoT Hub. It makes it easier for data collection, storage, and analytics. Google Cloud, it provides real-time analytics, machine learning. So usually Amazon and Google, they provide AI and machine learning capabilities to be integrated with IoT application. But of course, all of them are paid services. So when you build your application, you have the ability to use this commercial cloud with integrated services, or you can build cloud instances on yourself, like platform as a service, and then build these different type of data analytics on your own, depending on the complexity and the budget of your project. You have Arduino IoT Cloud. This is something that you can try with the Arduino boards. And TUI IoT Platform, this is one of the biggest Chinese companies for IoT market. I have introduced some of the devices that are available on Amazon or AliExpress. And this is good for quick setup for smart home devices and integrate easily. I think we reached the end of the lecture. Thank you. That's all for today. Any questions?